Hello there, and welcome to Sleepy Science Vault. Settle in. Take a slow, deep breath, and let yourself relax. We're going on a very long, very gentle journey tonight. Down, deep beneath the surface of the earth, to a place where rock becomes something else entirely. Where the solid ground beneath your feet is not quite as solid as it seems. Far below you, deeper than any mine, deeper than any tunnel ever drilled, the earth is alive. It has always been alive. Slowly, quietly, enormously alive. And it all begins in a place called the mantle. The mantle is a vast, ancient layer of rock, sitting deep beneath the crust we live on. It stretches down and down for thousands of kilometers. And within it, something remarkable is always happening. Very slowly, almost impossibly slowly. Rock is moving. In certain places deep within the mantle, hot material rises upward, the way warm water rises gently to the surface of a quiet bath. This rising, this slow upwelling, is one of the great engines that drives volcanic activity on our planet. As this hot rock climbs upward, something important happens. The pressure around it begins to fall. Pressure is one of the great forces controlling what happens inside the earth. Under enormous pressure, rock stays solid, even when it is searingly hot. But as that hot rock rises, as it moves toward shallower depths, the pressure eases. And with that release, the rock begins to melt. This process has a name. It is called decompression melting. And it happens quietly, invisibly, at places like mid-ocean ridges, where the plates of the earth are slowly pulling apart, and at rift zones, where the land itself is being gently pulled in two. In these places, the mantle rises to fill the gap, and as it rises, it melts. But there is another way that magma is born. On the floors of the deep oceans, great plates of rock are always moving, very slowly, over millions upon millions of years. Sometimes, one plate slides beneath another, sinking back down into the depths of the mantle. This is called subduction, and it carries something precious with it. Water, locked inside the minerals of that sinking plate. Water is carried down, deep into the hot mantle below. And water does something extraordinary. It lowers the melting point of the rock around it. Like salt on ice on a winter road. It encourages melting, even where melting might not otherwise occur. This is how arc volcanoes are born. The volcanoes that rim the Pacific Ocean, the Great Ring of Fire, they owe their existence, in large part, to water, carried down into the dark by sinking plates of ancient ocean floor. Something so simple, driving something so vast. And then there are the hotspot volcanoes. These are different. These rise not from the edges of plates, but from far within them. In certain places beneath the Earth's crust, the mantle produces a focused column of heat, a plume rising slowly upward, melting rock as it goes. As the great tectonic plates drift slowly over these stationary plumes, volcanoes form above them, erupt for a time, and then are carried away. A new volcano forms in its place, and then another, and another. Over millions of years, a chain of volcanic islands is left behind, like footprints, marking the slow, ancient path of a moving plate. Now, deep inside these systems, something subtle and beautiful is happening. When rock melts, it does not all melt at once. Different minerals, locked within that rock, each have their own melting point. Some surrender to the heat first, others hold on longer. This selective melting, this patient, gradual process, means that the first drops of magma to form are different in composition from the rock they came from. The melt carries some minerals more than others. It is enriched and changed by the very act of melting. And sometimes, that melting magma encounters older material, ancient crustal rock that was once carried down, subducted long ago, recycled sediments from ocean floors, absorbed into the melt. And this ancient material leaves a kind of fingerprint, a chemical signature, preserved in the erupted lava. Millions of years later, a memory written in rock. Once formed, the magma must find its way upward. And for a long time, geologists imagine this as a broad, slow rise, a wide column of melt seeping gradually through the rock above. But what deep seismic imaging has revealed is something more elegant, more focused. In many volcanic systems, the magma does not rise broadly. It finds narrow pathways, pipe-like channels, almost like veins, carrying molten rock upward with surprising efficiency. These narrow channels, focused and direct, can move magma from the depths of the mantle all the way to the crust above, faster than a broad, diffuse rise would allow. The melt is not spread thin. It is concentrated, guided upward. And so the journey begins. Deep, in the slow heat of the mantle, rock yields to warmth and released pressure, and becomes something fluid, something alive in a new way. It collects, it moves, it rises through narrow channels toward the world above. Let that image sit with you for a moment. Far below where you are now, this is always happening. Quietly, slowly, without any urgency at all. The earth, going about its ancient work, as it has for billions of years. Just breathe and rest. There is nothing you need to do. The earth is doing all the work tonight. Deep below, in the slow, warm dark, something is always beginning. Close your eyes a little more. Let your breathing slow. We left off deep in the mantle. where rock had softened and begun its long journey upward. Now, we follow it as it rises, slowly, steadily, through the great thickness of the Earth's crust. The first thing to understand is why magma rises at all. It seems almost too simple, but the answer is one of the most fundamental forces in nature. Magma rises because it is lighter than the rock around it. The solid crust, dense and ancient and heavy, presses in from all sides. But the magma, molten and fluid, is less dense than the walls that surround it. And so, it floats upward, the way a bubble of air rises, through still, dark water. Slowly, inevitably. But the crust is not an open space. It is not simply waiting to be filled. It is solid and thick, and the magma must find its way through. So it looks for weakness. Every piece of rock, no matter how solid it appears, contains fractures, ancient cracks, lines of stress, left behind by millions of years of pressure and movement and slow geological time. And it is along these fractures, these pre-existing lines of weakness, that magma finds its path. The great tectonic forces that shape the Earth, the same forces that build mountains and pull continents apart, are constantly pressing on the rock of the crust, loading it with stress. And that stress determines which fractures open, which pathways become available, where the magma is invited to go. In this way, the path a volcano takes is partly written long before the eruption ever begins. The tectonic history of a region, the faults laid down over millions of years, guide the magma, almost like a map. And because of this, eruptions do not always come from a single central point. Sometimes the magma follows a long fracture, a line in the crust, and instead of one vent, a whole series of openings appears, side by side, stretching across the landscape. These are called fissure eruptions, and they are among the most extraordinary sights in the volcanic world. A curtain of fire, rising from a crack in the earth, stretching for kilometers. But let us stay underground for now. Let us follow the magma more closely as it moves through the crust. As magma forces its way upward, it does something remarkable to the rock around it. It pushes, and the rock, rather than simply melting out of the way, breaks in the shallower, cooler parts of the crust. Rock behaves in a brittle way. Like cold glass, it fractures rather than bends. And the magma exploits those fractures, pushing them open, widening them, flowing in. These magma-filled fractures have a name. They are called dikes. Thin sheets of molten rock, forced into cracks in the crust, sometimes only a meter or two wide, but stretching for kilometers in height and length. quiet, hidden structures buried within the earth. And sometimes the magma does not travel vertically. Sometimes it finds a horizontal weakness, a boundary between two rock layers, and it spreads sideways, like water seeping between pages of a book. These flat, horizontal sheets of magma are called sills, and they can spread for great distances, quietly, invisibly, miles beneath the surface. What this means is that beneath a volcano, the plumbing is rarely a simple pipe. It is a network, a web of dikes and sills, intersecting and connecting, some vertical, some horizontal, some branching, some dead-ending in the rock. A hidden architecture of astonishing complexity. And this network has a remarkable ability. Magma in one part of the system can suddenly be connected to magma in another part. A sill spreading sideways beneath a volcano can reach a separate pocket of stored melt kilometers away and join them, allowing a sudden pulse of magma to move laterally, sometimes over many kilometers, in a very short geological time. This is one of the reasons volcanoes can surprise us. An eruption does not always come from directly below. The magma may have traveled sideways through a network of sills and dikes before finding its way to the surface from a place no one expected. Now, as we go deeper into the earth, something else changes. At greater depths, the rock is hotter and under more pressure. And hot, pressurized rock does not break like cold glass. It bends. It flows. Very, very slowly, like warm wax. This is called ductile flow, and it means the magma, at deeper levels, does not fracture its way through the crust. It moves through rock that yields and deforms around it, quietly, plastically, without the sharp cracking of brittle fracture. So the magma, on its long journey upward, travels through two very different kinds of crust. Deep below, it moves through warm, yielding rock that flows gently around it. Then, as it rises higher into cooler, stiffer crust, it begins to fracture its way forward, breaking open new pathways, pushing dikes into the rock. And all along the way, it may pause. There are places in the crust where rock of one type sits atop rock of a very different type, where a dense, stiff layer caps a softer one below. And when magma rising through the softer rock meets that stiff layer above, it may find it cannot push through. Not yet. And so it spreads out beneath that barrier, pooling, waiting, collecting, sometimes for years, sometimes for thousands of years, biding its time. But the earth is never truly still. Earthquakes ripple through the crust, loading and unloading stress. opening fractures that were closed, closing fractures that were open. And these stress changes, these distant earthquakes and tectonic shifts, can reach down into the earth and unlock a pathway that was closed. Suddenly, the magma that was waiting has somewhere to go. A pulse of melt, injected upward, moving through a newly opened fracture, beginning its final journey toward the surface. And so the rise of magma is not a simple, steady flow. It is a story of patience and opportunity, of force and yielding, of a liquid finding its way through a world of solid rock, guided by fractures, shaped by stress, pausing when it must, moving when it can. All of this is happening somewhere beneath the earth right now. In the dark, in the silence, miles below the surface, magma is finding its way. Slowly, unhurriedly, following paths laid down long ago. And you, resting here, breathing slowly, do not need to follow it any further tonight. Let it rise without you. Let the earth do its quiet work. You are warm and still, and the world beneath you is moving, just barely, just enough to remind you that everything is alive, even in the deep, even in the dark, even in the silence. Rest now. There is so much more to discover, but it will wait for you. It has been waiting for millions of years. A little longer will not matter at all. Let your body sink a little deeper. Wherever you are resting now, feel the weight of your arms, the softness of your breath. We have followed the magma a long way already. Up through the deep mantle, through networks of dikes and sills, through fractures and slow, yielding rock. And now, it begins to slow. Somewhere in the middle of the crust, several kilometers below the surface, the magma finds a place to rest. Not permanently, not forever, but for a while. A long while. Here is why. The magma is rising because it is lighter than the rock around it. We know this now. But the crust is not the same everywhere. As the magma rises higher, it eventually encounters rock above it. That is dense, heavier than the magma itself. And that dense roof of rock acts like a lid. The buoyancy that carried the magma upward is no longer enough to push through. And so the magma pools. It spreads outward, filling the space available to it, growing slowly, accumulating, waiting. This is how a magma chamber begins. But not just anywhere will do. The crust has its own preferences, its own tolerances. Too deep, and the rock is so hot and pressurized that the magma simply dissipates, absorbed back into the warmth around it. Too shallow, and the rock is too cold and stiff, too brittle to accommodate a growing body of melt. But in between, at just the right depth, usually several kilometers beneath the surface, there is a kind of sweet spot, a zone where the pressure is just right, where the rock is strong enough to hold the magma in place, but yielding enough to let it accumulate, where volatiles dissolved in the melt behave in ways that allow storage, rather than immediate eruption. This is where magma chambers live. In that narrow, patient window, between too deep and too shallow, between dissipation and eruption, sitting quietly, storing heat and time. Now, for many years, scientists imagine magma chambers as simple things. A sphere, or an oval, of liquid rock, sitting beneath a volcano like a great underground lake. Hot, molten, waiting to be released. It was a tidy picture, a satisfying one. But the Earth, as it so often does, turned out to be far more interesting. When modern seismic imaging began to peer inside these systems, when the tools became sensitive enough to see into the deep rock, what they found was not a single chamber, not a simple, round reservoir of liquid. What they found was something far more intricate. Branching networks, so like lenses stacked at different depths. Narrow conduits connecting one body of melt to another. Multiple reservoirs, some deep, some shallow, some large, some small, all connected, all part of a single, vast, hidden system. In some volcanoes, there appear to be two distinct reservoirs. A deep one, sitting far down in the crust, slowly accumulating fresh magma from the mantle below, and a shallow one, sitting closer to the surface, more immediately connected to the vent above. These two reservoirs communicate with each other, slowly, intermittently. When fresh, hot magma from the deep reservoir pushes upward into the shallow one, it changes things. It adds heat. It adds pressure. It stirs what was settled. And it is often this interaction between the deep and the shallow that sets the clock ticking toward an eruption. But even the idea of a reservoir, a chamber, a room full of liquid magma, is more complicated than it first appears. Because much of what sits beneath a volcano is not fully liquid at all. Imagine a mixture of crystals and melt, semi-solid, like a very thick slurry, or wet sand, or the inside of a half-frozen river, where ice and water coexist. Neither fully one thing, nor fully the other. This is called crystal mush, and it is one of the most important concepts in understanding what volcanoes truly are. Beneath many of the world's great volcanoes, there is not a lake of liquid magma. there is a vast body of crystal mush, occupying an enormous volume of the crust. Crystals grown slowly over thousands of years, locked together in a semi-rigid framework, with liquid melt filling the tiny spaces between them, like water filling the spaces between grains of sand. Most of the time, this mush just sits there, cool enough to hold its shape, hot enough to never fully solidify. Patient, enormously patient, storing heat, storing melt, storing potential across timescales that dwarf human civilization. And because the melt is distributed through the mush, spread across countless tiny pockets, rather than gathered in one place, it is harder to detect, harder to see, harder to reach. But then, something changes. A pulse of fresh, hot magma rises from below, injected into the base of the mush zone, bringing new heat, new volatiles, new energy, and the mush begins to wake. The temperature rises, just slightly, just enough. The crystals at the edges of the mush begin to loosen. The interstitial melt, the liquid trapped between them, begins to move. What was locked becomes fluid. What was stored becomes available. A small increase in temperature, a modest injection of new magma, can mobilize a vast amount of stored melt very rapidly. In geological terms, what seemed solid and quiet becomes dynamic. What seemed permanently frozen in the rock begins to flow. This is one of the great revelations of modern volcanology. The melt beneath a volcano is not simply sitting in a chamber, waiting. It is woven through a fabric of crystals, distributed, stored, alive in a quiet, distributed way. And when conditions are right, it can be called back together, gathered, mobilized, with surprising speed. Some of these mush systems are ancient. They have been accumulating, growing, evolving for hundreds of thousands of years. They are not young. They are not simple. They are living libraries of the volcanic history of a place, written in chemistry, in crystal structure, in isotopic ratios, in the arrangement of minerals, frozen in place until the next awakening. And all of this is happening in silence, in darkness, miles beneath the surface, beneath mountains, beneath plains, beneath ocean floors. Great, slow systems, breathing in geological time. Let that settle over you like a warm, heavy blanket. The idea that beneath so much of the solid ground, there are these hidden, ancient systems. Not violent, not urgent, just present, patient, persisting, You are resting above a planet that has been storing heat and melt and potential for billions of years. It is in no hurry, and neither are you. Let your thoughts slow, the way magma slows when it finds a resting place deep in the crust, pooling gently, settling, releasing the urgency of the journey. For now, just resting. There is more to come. So much more. But the mush will wait for us. It always does. It has been waiting long before any of us were here. And it will wait long after. Just breathe and let the deep earth carry you gently into the quiet. Breathe in slowly and out. We are still underground, still in the deep, quiet world, beneath the surface of things. There is no need to rush. The magma is not rushing, and neither are we. We left off inside the crystal mush, that vast, semi-solid world of crystals and trapped melt, sitting in the dark, storing heat, storing time. And now we go deeper into what happens there. Inside these hidden chambers, across the long, slow years. Imagine a mush zone, sitting in the crust, perhaps 5 kilometers below the surface. It has been there for a very long time. Centuries, perhaps millennia, slowly cooling at its edges, slowly crystallizing, holding most of its melt, locked between mineral grains, quiet. And then, from somewhere below, a new pulse of magma arrives. Fresh, hot, less crystallized than what is already there. It pushes up into the base of the mush, and the effect is immediate. In geological terms, the new magma brings heat, and that heat spreads outward into the cooler mush above. The crystals at the boundary begin to loosen. The frozen edges begin to soften. Melt that was locked between crystals begins to move, to gather, to reconnect. A system that seemed permanently at rest stirs, and what was distributed and scattered begins to come together. This is one of the ways volcanic systems stay alive. Not through constant activity, not through endless eruption, but through these periodic reinjections, these pulses of new heat, arriving from below, keeping the mush just warm enough, just mobile enough, to persist across thousands of years. And in some systems, the melt never fully gathers into a true chamber at all. It remains distributed, scattered through the crust in tiny pockets, here and there, each one holding just a small fraction of melt, a few % liquid, the rest all crystal. These small, distributed pockets are not dramatic. They are quiet, hidden even from most seismic instruments. But they are real. And when the conditions are right, when a new injection of heat arrives, or when tectonic stress shifts just so, these scattered pockets can be remobilized, drawn together, and fed upward to feed an eruption from a system that appeared to barely exist at all. Now, in larger systems, where melt is more abundant, something else begins to happen. Something that turns the magma chamber into a living, moving world, all on its own. Heat does not distribute itself evenly. Hot magma at the base of a chamber is less dense than the cooler magma above it, and so it rises, just as warm air rises in a room, just as warm water rises in a pot. This movement, this slow, continuous rising of hotter material and sinking of cooler, crystal-laden material, is called convection. And in a large magma chamber, it operates continuously, turning the chamber into a slowly churning system. The hotter melt rises through the center, spreads outward at the top, cools and crystallizes at the edges, and sinks back down along the walls. A slow, circular motion, taking perhaps years to complete a single cycle, or decades, or centuries, but always moving, always redistributing heat, always keeping the chamber thermally alive. This convection does more than move heat. It moves chemistry. It carries certain elements upward and lets others settle downward. It distributes crystals through the chamber or concentrates them at the floor. It is one of the great engines of change inside a magma body, working silently over geological time. And as convection works, as crystals form and settle, as lighter melts rise and heavier ones sink, the chamber begins to develop layers. This is called compositional stratification, and it is one of the most important things that happens inside a long-lived magma chamber. At the bottom, the densest material accumulates, crystal-rich, heavy, dark in composition, rich in iron and magnesium. At the top, the lightest melt gathers, pouring crystals, rich in silica, rich in dissolved gases, lighter, more buoyant, more volatile. The chamber becomes layered, like a slowly settled jar of mixed liquids, each layer with its own chemistry, its own density, its own character. And this matters enormously for what happens when an eruption begins. If the volcano taps the top of the chamber, it draws out that light, gas-rich melt, full of dissolved volatiles ready to expand. And an eruption fed by that upper layer can be very different in character from one that draws on the denser material below. The upper layer, released suddenly, can produce explosive, dramatic eruptions, while the deeper, crystal-rich material might flow more slowly, more quietly. One chamber, one volcano. But the story of its eruption depends enormously on which layer is tapped and when. But the layering is not always simple. It is not always a neat stack, because the chamber is not uniform. Even within a single magma body, different parts can be at different temperatures, different stages of crystallization. Some pockets within the chamber remain largely molten, while adjacent pockets, just a short distance away, are nearly solid. A mosaic of states, some liquid, some mushy, some almost rock, all coexisting, all part of the same system. And this produces something remarkable. When an eruption finally taps the chamber, it may draw material from different parts, at different stages of evolution, different compositions, different temperatures, mixed together as they travel upward. The products of a single eruption, a single event, can carry the signatures of multiple magma types, whispers of the chamber's internal complexity, preserved in the lava, for geologists to read millions of years later. Over longer timescales, something even more gradual is happening. Deep in the system, the freshest magma arriving from the mantle is rich in certain elements: iron, magnesium, calcium. But as magma sits in the shallow crust, as it crystallizes and evolves, it slowly becomes enriched in silica, in sodium, in potassium, in the elements that are left behind when crystals form and settle out. This long-term chemical evolution, playing out over thousands of years, creates a kind of depth profile. Deeper magma with one chemistry, shallower magma with another. A gradient of composition, from root to roof. And as the volcano erupts over its lifetime, drawing on different parts of this gradient, at different times, the chemistry of its lava slowly changes, telling the story of the chamber's evolution. In the rock record, a diary written in minerals. So when you think of a magma chamber now, let go of the simple image. The round underground lake, the neat reservoir waiting to be emptied. Replace it with something richer, something more alive. A layered world, slowly convecting, thermally alive, chemically evolving, patchy and complex, different in every corner. A place where crystals grow and settle, where heat rises and falls, where gases accumulate near the top, where new injections of hot magma arrive from below, disturbing the settled layers, stirring the mush, resetting the slow clock. All of it in darkness, all of it in silence, all of it patient. Let that world exist quietly, somewhere far beneath you. As you rest, you do not need to hold it all in your mind. Just let it be there, the way it has always been there, beneath the surface of things, complex and beautiful, and utterly unhurried. Your breath is slow now. Your body is heavy and still. The magma is still moving. Somewhere below, convecting in its slow circles, crystallizing at its edges, dreaming in its own geological way. And you are drifting gently downward into rest. Let the layers settle, the way the chamber settles, quietly, one by one, into the warm, patient, dark. Let yourself settle even deeper now, into whatever is holding you. Feel the stillness, the warmth, the quiet weight of rest. We are going back underground, back into the chamber, back into that layered, living world. But this time, we are going to watch it change. Nothing underground stays the same forever. Not even magma. Sitting in the dark, in its quiet chamber, far below the surface. Even there, even in that slow, hidden world, transformation is always underway. It begins with crystals. As magma sits in its chamber, cooling gradually at the edges, certain minerals begin to solidify out of the melt. They grow slowly, adding layer upon layer. The way a tree adds rings, the way ice thickens on a still pond. In winter, these crystals do not form all at once. They grow over time, and as the conditions in the chamber change, as the temperature shifts, as the chemistry of the surrounding melt evolves, the crystal changes too. Each new layer that forms reflects the conditions at that moment, that particular temperature, that particular composition, that particular point in the chamber's long history. And so a single crystal, perhaps no larger than a grain of rice, becomes a record, a tiny archive of everything the magma experienced while it was stored. Geologists can look at these crystals under a microscope and see the zones, light and dark bands, each one a chapter in the chamber's story. A shift in chemistry here, a change in temperature there, evidence of a new pulse of magma arriving, evidence of a period of slow cooling. All of it written in the layered structure of a single mineral grain. This is called crystal zoning, and it is one of the most intimate records we have of what happens inside a volcano, long before it ever erupts. But the crystals are not just passive recorders. They are active participants in the ongoing chemistry of the chamber. While a crystal sits in the melt, chemical exchange continues. Elements move back and forth between the crystal and the surrounding liquid. Sometimes the crystal grows, adding new material from the melt. Sometimes conditions change, and the crystal begins to dissolve. Edges softening, boundaries becoming irregular, material returning to the melt it came from. A crystal that began growing in one set of conditions may find itself partially dissolved when hotter magma arrives from below, and then begin growing again. Under new conditions, its surface a record of interruption, of dissolution and regrowth, of the chamber's own turbulent inner life. And sometimes, the change that comes is not subtle. Sometimes, what arrives from below is not just a quiet pulse of heat, but a whole new body of magma. Imagine two magmas. One that has been sitting in the shallow chamber for a long time, cool and evolved, rich in silica, heavy with crystals, slow and viscous. And then, rising from deeper in the system, a new injection of magma, fresher, hotter, less evolved, more fluid, more primitive. These two magmas meet, and the meeting is not always gentle. The hot new magma pushes into the cooler resident melt. Their temperatures are different. Their compositions are different. Their densities are different. They do not mix easily. In some cases, they swirl together incompletely, like oil and water being stirred, producing hybrid textures, streaks and blobs of one magma type, enclosed within the other, frozen in place. When the rock finally solidifies, these features, preserved in ancient lavas, tell geologists that mixing happened here, that two magma types met and became something new together. In other cases, the hot new magma does something even more dramatic. It brings so much heat that it begins to melt the crystal mush around it. The semi-solid framework of crystals that had been patiently accumulating for centuries softens, loosens, and portions of it return to the melt. A system that was cooling and solidifying is suddenly recharged, reheated, reinvigorated. More melt becomes available. More volatiles are released. Pressure in the chamber begins to rise, and the volcano above begins to stir. These recharge events, these injections of new, hot magma from below, are among the most important triggers of volcanic unrest, an eventual eruption, and they leave signals that scientists on the surface can sometimes detect. When new magma pushes into a system, it disturbs the rock. It opens new fractures, shifts existing ones. The crust around the chamber adjusts, crackles, settles into new configurations. And each tiny fracture, each small adjustment, produces a small earthquake. These earthquakes are usually too small to feel, but sensitive instruments, seismometers placed around the volcano, can detect them. A swarm of small earthquakes, hundreds or thousands of them, clustered in time and space, is often the first sign that something is changing underground, that new magma is on the move. And alongside the seismic signals, the gases change too. Fresh, hot magma carries dissolved gases. Sulfur dioxide, carbon dioxide, water vapor. And as it rises into the system, as pressure decreases, these gases begin to separate from the melt, rising through the rock, finding their way upward, seeping out through the ground, or venting from the crater above. A sudden increase in sulfur dioxide, measured at the surface, is often a sign that new, undegassed magma has arrived in the shallow system, fresh from the deep, still carrying its full load of volcanic gases. Together, the seismic swarms and the changing gas chemistry are like the volcano's vital signs, the heartbeat and breath of a system that is reawakening. In the magma supply, the flow of new material rising from below is rarely steady. It does not arrive in a constant, even stream. It comes in pulses. A pulse of new magma, arriving in the chamber, brings its own temperature, its own composition, its own cargo of dissolved gases. It disturbs what was settled, stirs what was still, adds pressure where pressure was building, or relieves it, depending on the geometry, depending on the timing, depending on 100 factors, all interacting at once. And because the supply is pulsed, the eruptions that result are irregular too. Not a steady drip, but an episodic rhythm. Periods of quiet, broken by periods of unrest, repose, and renewal, stillness, and stirring. This irregularity is part of what makes volcanoes so difficult to predict. Each pulse is different. Each recharge event changes the system in ways that are never quite the same twice. The chamber evolves. The mush changes. The stress field shifts. And the volcano emerges from each cycle, subtly different from what it was before. So the magma underground is never truly static, never simply waiting. It is changing, chemically, thermally, structurally. Crystals are growing and dissolving. New melt is arriving and mixing. Gases are exsolving and rising. The chamber is convecting and layering. All at once. All in the dark. All in geological silence. A living system, breathing in its own slow way. Let that be the last image you hold tonight, before you let it all go. A chamber in the dark, quietly alive. Crystals recording history in their layers. New magma arriving in pulses. The system adjusting. Slowly. Continuously. Never finished. Never truly still. And you, above all of that, resting, breathing, your own quiet rhythm, matching the slow pulse of the earth. There is no urgency here, no hurry, The next pulse will come when it comes. The crystals will grow at their own pace. The melt will mix in its own time. And you will drift gently on the surface of a world that is always slowly becoming something new. Rest now. Let the chemistry settle. Let the layers form. Let the deep earth do what it has always done. While you sleep, let the weight of your body settle a little more into the stillness beneath you. There is nowhere to be, nothing to do. Just this. Just the quiet and the slow, deep world we have been exploring together. We have watched magma form and rise and rest and change. And now we are going to watch it do something even more subtle. Something that happens over enormous stretches of time. Something that transforms not just the magma itself, but everything around it. We are going to watch the crust be remade. It begins with a pulse, a small injection of magma, rising from below, pushing into the cool rock of the crust, finding a space, filling it, and then cooling, solidifying, becoming rock itself. This single pulse, on its own, would make only a small intrusion, a thin dike, a narrow sill, a modest blob of solidified melt. Unremarkable. But it is not alone. In the great volcanic systems of the world, magma does not arrive just once. It arrives again, and again, and again, pulse after pulse. Each one small, each one adding just a little more material to what is already there. Over thousands of years, over hundreds of thousands of years, these small, incremental additions accumulate, and slowly, something enormous grows. This is how the great intrusive bodies of the crust are built. The plutons, the batholiths, masses of solidified rock, sometimes hundreds of kilometers across, sometimes exposed at the surface by millions of years of erosion. The roots of ancient mountains, laid bare. They were not placed all at once. They were not injected in a single catastrophic event. They grew incrementally, pulse by pulse, over geological timescales, patient accumulations of countless small arrivals. And as each new pulse of magma arrives, something happens at its edges. Something that changes both the magma and the rock around it. The magma is hot, searingly hot, and the crustal rock it intrudes into is cool and solid and composed of minerals that were never meant to coexist with liquid rock. At these temperatures, the magma begins to react chemically with the rock around it. It absorbs material from the walls, from the floor, from the roof. Fragments of crustal rock break off into the melt and dissolve, their chemistry becoming part of the magma, changing it, enriching it with elements it did not carry from the mantle. This process is called assimilation, and it is one of the ways that the composition of a magma changes on its journey from source to surface. The magma arrives with one chemistry and leaves, or erupts, with another, carrying the fingerprints of every rock it touched, every layer it absorbed, every wall it dissolved, on its way through the crust. And the crustal rock is not unchanged either. Around every hot intrusion, the surrounding rock is transformed. The heat radiates outward, slowly, like warmth spreading from a fire, through the cold rock. In all directions, minerals that were stable at low temperatures find themselves suddenly in a different world. They respond by recrystallizing, reorganizing their atomic structure, growing new mineral forms, more suited to the new temperature. This transformation of rock by heat, without the rock actually melting, is called thermal metamorphism, and it creates a halo around the intrusion, a zone of altered, transformed rock, grading from intensely changed near the contact to barely affected further away. In ancient, deeply eroded terrains, geologists can walk through these halos, moving outward from the old intrusion, watching the rocks change beneath their feet, from intensely recrystallized at the center to progressively more normal. As the distance grows, a frozen record of heat radiating outward through ancient rock. But the heat does more than recrystallize. It also cracks. As heat moves through cold rock, different parts of the rock expand at different rates. Minerals expand. Boundaries are stressed, and the rock develops tiny fractures, networks of microcracks, threading through the transformed zone, like a fine web, spreading outward from the hot intrusion at the center. These microfractures are small, individually insignificant, but together, they create something important: permeability, pathways through which fluids can move. And fluids, in the world of a cooling intrusion, are everywhere. As the magma cools, as it crystallizes, it releases the volatiles it was carrying: water, carbon dioxide, sulfur, chlorine, fluorine. These gases, these hot, reactive fluids, are expelled from the crystallizing melt, and they have nowhere to go but outward, into the fractured rock. And as they move, they carry something with them: magma, during its long residence in the crust, tends to concentrate certain elements that do not fit comfortably into the crystal structures forming around them, that are excluded from the minerals growing in the melt. These are called incompatible elements and volatile compounds, and they accumulate in the remaining liquid, growing more and more concentrated as crystallization proceeds. When the fluids finally leave the crystallizing magma, they carry these concentrated elements with them, dissolved in hot, acidic solution, moving through the fracture networks in the surrounding rock. And as they move, they cool. They react with the minerals in the rock walls. The chemistry changes. The solubility of the elements they carry drops, and they precipitate, drop out of solution, and crystallize in the fractures, in the pores, in every available space. What forms in those fractures can be extraordinary. Veins of quartz, laced with metal sulfides, concentrations of copper, gold, silver, molybdenum, tin, tungsten, elements that were dispersed invisibly through kilometers of rock, gathered by fluids, transported and deposited in narrow veins, in localized zones, in the halos around ancient intrusions. Many of the world's great ore deposits, the copper mines of Chile, the gold deposits of Nevada, the tin mines of Cornwall, owe their existence to this process, to the quiet work of hot fluids, moving through fractured rock, around a cooling magma body, concentrating, depositing, leaving behind treasure in the rock, in the volcanic gases, those that reach shallower levels, those that interact with groundwater and surface fluids. They too react with the rock, forming acidic solutions that dissolve and alter, and sometimes redeposit minerals in new forms, new veins, new concentrations, at shallower depths. A secondary layer of enrichment, built on top of the deeper one. So a volcanic system is not just a machine for making eruptions. It is a chemical factory, transforming the rock around it, concentrating elements, building ore deposits, remaking the crust from the inside out, quietly, continuously, over millions of years. The mountains we mine, the metals in our phones, in our wires, in our coins, many of them began as trace elements, dispersed through mantle rock, concentrated by the patient work of magma and fluid and heat and time. Let that thought expand gently in your mind. The deep connection between the volcano and the world we have built, between the ancient work of magma and the objects in our hands. All of it. Beginning in that slow, dark place, miles beneath the surface, where rock melts and rises and transforms everything it touches. You are part of a planet that has been doing this work for 4.5 billion years. Building, recycling, transforming, concentrating, patiently, without interruption, without urgency. And you, resting now, are the beneficiary of all that patient work. The iron in your blood came from stars and was concentrated here by geological processes just like these. Let that be the last thing you hold before you let it all drift away. That you are connected to all of this, not just observing it, but part of it. The cooling, the crystallizing, the slow release of heat into the rock, into the ground, into the world above. And now, let your own warmth settle. Let your own chemistry come to rest. Let the deep processes carry on without you. For a while, you have come a long way tonight. From the mantle, through the rising magma, through the chamber, through the crystal mush, and now into the rock itself, transformed by heat, threaded with veins, slowly becoming something new. Sleep now. The earth will keep working. It always does. It has never stopped. Not once. In 4.5 billion years. And it will not stop tonight. While you rest, let it carry on. In the deep, in the dark, in the quiet, while you drift slowly away. Let your breathing slow, just a little more, in and out. There is no rush. There has never been any rush. We have all the time in the world. We have spent so long underground now, watching the magma form, and rise, and rest, and change. And something has been building, very quietly, through all of that time. Something dissolved, hidden, invisible, locked inside the melt itself. Tonight, we turn our attention to it. Magma, as it sits in its chamber, is not simply molten rock. It carries within it dissolved gases, water vapor, carbon dioxide, sulfur dioxide, chlorine, fluorine, and others. All of them invisible. All of them dissolved into the melt. The way carbon dioxide is dissolved in a bottle of still water. Under pressure. You cannot see them. You would not know they were there if you looked at the magma from the outside. But they are there, waiting. And what keeps them dissolved? What keeps them locked invisibly inside the melt is pressure. Deep in the earth, the pressure is enormous. Miles of rock above, pressing down, squeezing the magma, keeping those gases in solution, contained, quiet. But as the magma begins to rise, as it moves upward through the crust, the pressure above it decreases, and at a certain depth, at a certain pressure threshold, the gases can no longer stay dissolved. They begin to come out of solution. The way bubbles form when you open a pressurized bottle or lift a glass of sparkling water slowly into the light. This moment, this depth at which the gases begin to separate from the melt, is called the exsolution depth. And it is different for different gases, different for different magma compositions. Water, one of the most abundant volatiles in magma, begins to exsolve at different depths, depending on how much of it was dissolved in the melt to begin with. A magma rich in water will begin to exsolve at greater depth, deeper underground, while a drier magma may not begin releasing its water until it is much closer to the surface. This seemingly small difference has profound consequences for what happens next. As the gases leave the melt, they form bubbles, tiny at first, barely visible, scattered through the magma, like the first fine bubbles that appear in a glass of sparkling water just poured. These tiny bubbles begin to grow as the magma continues to rise, as pressure continues to fall. More gas exsolves, and the bubbles expand. The magma, which was once a dense, bubble-free liquid, becomes something different, something lighter, something more complex. A foam, almost. A melt laced with countless small gas pockets, each one growing, each one adding to the buoyancy, each one contributing to the upward drive. But the story of these bubbles is not simple. In large magma chambers, the behavior of gas can be subtle and sometimes counterintuitive. Bubbles, once they form, are less dense than the surrounding melt, and so they rise, just as bubbles always rise. Through any liquid, they drift upward, through the magma, toward the top of the chamber. And over time, the upper part of the chamber becomes enriched in gas, a layer of bubble-rich, gas-saturated melt, accumulating near the roof, while the deeper parts of the chamber remain less gassy, more dense, more stable. This separation, this tendency of gas to gather at the top, means that the uppermost magma in a chamber is often the most volatile, the most pressurized, the most ready. And the bubbles themselves do not always stay small. As smaller bubbles drift upward, they encounter other bubbles. They meet and merge, coalescence, growing into larger bubbles, and larger ones still. In some systems, particularly in magmas that are more fluid, less viscous, these merged bubbles can become substantial, large pockets of gas, rising more quickly through the melt, sometimes forming elongated slugs of gas, moving upward through the conduit toward the surface. These gas slugs, rising through the magma, are one of the mechanisms behind a particular type of volcanic behavior, a rhythmic, regular, almost gentle kind of eruption, where bursts of gas arrive at the surface, one after another, each one a slug that has risen from below. But gas does not always escape. Sometimes, under the right conditions, it can return. If the pressure in a system increases, perhaps because new magma has arrived, perhaps because the conduit above is partially closed, the solubility of gas in the melt increases, and bubbles that had already formed can be reabsorbed, dissolved back into the melt, as if they had never existed. This redissolution, this quiet reabsorption of gas back into the magma, is one of the more subtle and counterintuitive behaviors of volcanic systems. It means that a volcano can appear to be building toward eruption, and then, quietly, stand down, the gas retreating back into the melt, the pressure easing, the system settling back into repose, at least for a while. Now, alongside all of this, there is another property of magma that controls everything about how it will eventually behave. At the surface, viscosity. Viscosity is resistance to flow. Honey is more viscous than water. Cold honey is more viscous than warm honey. Thick mud is more viscous than thin mud. And magma ranges from remarkably fluid to almost impossibly thick, depending on several things, all happening at once. Composition matters enormously. Magmas rich in silica, like rhyolite, are highly viscous. The silica molecules form long, tangled chains in the melt, resisting flow, resisting movement, resisting the escape of gas. Magmas pour in silica, like basalt, the dark, fluid lava of Hawaii, of Iceland, of the ocean floors, are much less viscous. They flow easily, almost like thick syrup, spreading across the ground, finding every low point. But composition is not the only thing. Temperature plays a role too. Hotter magma is less viscous. more fluid, more willing to flow, cooler magma, more crystallized, more sluggish, and crystals themselves, suspended in the melt, add to the viscosity. A crystal-rich magma, thick with suspended mineral grains, moves far more reluctantly than a crystal-poor one, even if the composition is similar. So viscosity is a product of composition and temperature and crystal content, all three acting together, producing a magma that is either willing to flow or resistant to it. And it is the combination of viscosity and gas content that ultimately determines how a volcano erupts. Think of it this way: a low viscosity magma, fluid and mobile, loaded with gas, will allow those bubbles to rise freely, to escape easily, to vent gently at the surface, without much drama. The gas leaves quietly. The lava flows. The eruption is effusive. But a high viscosity magma, thick and resistant, loaded with the same gas, does not allow easy escape. The bubbles cannot rise freely. They are trapped, held in place by the thick, resistant melt around them. Pressure builds and builds and builds until it cannot build anymore. And then the release is not gentle. The magma does not flow. It fragments. It is torn apart by the expanding gas, shattered into droplets and shards, hurled upward at enormous velocity in an explosive eruption. This is why volcanoes, all fed by the same deep earth, can behave so differently from one another. One pours out gentle rivers of lava. Another explodes with devastating force. The difference often comes down to these two things: the gas and the viscosity, working together or against each other. And all of this is being set up far underground before a single drop of lava ever reaches the surface. The viscosity established as the magma evolved in its chamber. The gas content accumulated over centuries of storage. The bubble networks forming. The pressure building. Quietly. Patiently. In the dark. The eruption, whatever form it takes, is just the final chapter of a story that began miles below, long before. Let that thought drift through you, gently, the way a bubble drifts upward through still liquid, unhurried, following its own slow path toward the surface. You have been following this story for a long time now. Down through the mantle, up through the crust, into the chamber, through the crystal mush, through the chemical transformations, and now into the very gases that give a volcano its voice. You know this world now, in a way that most people never do. You have been inside it, felt its slowness, its patience, its extraordinary complexity. And now, you can let it go. Let the bubbles rise without you. Let the viscosity do what it will. Let the pressure build or ease in its own time. You are at the surface, warm and still, and breathing slowly. Above all of it, resting on the thin skin of the earth, while far below, the slow, ancient work continues, as it always has, as it always will. Sleep now. The gases are rising. The pressure is finding its own level. Everything is in motion, and everything is fine. Just breathe and drift, and let the deep earth hold you gently from below. Let yourself be still, completely still, the way the earth is still on the surface, while everything moves far below. We have watched the magma rise. We have watched the gases form, the bubbles gather, the pressure build. And now, we begin to approach something new. The moment when all of that begins to move toward the surface, toward release. But even this, even the approach to eruption, is slower and quieter and more subtle than you might expect. Let us begin with what happens to the magma itself as it rises through the final kilometers toward the surface. We know that as magma ascends, pressure falls, and as pressure falls, gases come out of solution, bubbles form and grow. But in certain magmas, particularly those rich in silica, rich in dissolved water, the bubble growth is extraordinarily rapid. Imagine a melt, thick and viscous, carrying enormous amounts of dissolved gas. As it rises, as pressure drops, the gas tries to escape, tries to form bubbles, tries to expand. But the melt is so viscous, so resistant to flow, that the bubbles cannot rise freely, cannot escape ahead of the magma. They are trapped, and so they expand where they are, inflating the magma from within, like countless tiny balloons, all inflating at once, inside a material too thick to let them go. The magma becomes a foam, a rigid, glassy foam, stretched thin between expanding bubbles, locked into place by rapid cooling. As it rises into shallower, colder levels of the crust. And what you get when that foam solidifies is pumice. Pumice. That strange, pale rock, so full of bubbles that it floats on water, lighter than almost any other rock. A frozen record of gas trying to escape from a magma that was too thick to let it go easily. Each tiny hole in a piece of pumice was once a bubble, a pocket of volcanic gas, trying to reach the surface, frozen in place. At the moment the melt solidified around it, and in the most rapid ascents, in magmas rising very quickly, under extreme decompression. The quenching is even faster. The melt does not even have time to form bubbles. It simply freezes in an instant, chilled so rapidly that it solidifies as glass. Volcanic glass. Sharp, transparent, thin as a razor. This is how obsidian forms, and how the finest volcanic ash forms. Tiny shards of glass, formed by decompression so rapid that the melt had no time to do anything but freeze. Now, all of this rising magma, all of this expanding gas, all of this pressure building in the conduit, exerts force on the rock around it. And sometimes, that force exceeds the strength of the rock itself. When the pressure of the gas inside the magma, or inside the pores and fractures of the surrounding rock, becomes greater than the rock can withstand, the rock breaks. Not gradually, not slowly, but fractures, opening new pathways, releasing pressure, in a process called magmatic hydrofracturing. The magma and its gas literally crack open their own pathway through the last few kilometers of solid crust, forcing new conduits where no pathway existed before. And below, something equally dramatic can happen to the chamber itself. If an eruption is large enough, if magma is withdrawn from the chamber rapidly, the chamber walls and roof can no longer support themselves. The roof of the chamber, unsupported from below, weakened by the loss of the magma that was holding it up, begins to crack and fracture and ultimately collapse. This is how calderas form. Those vast, circular depressions, miles across, that mark the sites of the greatest eruptions. Not the cone of a volcano, but the collapsed roof of an emptied chamber, sunk into the space below. A landscape defined not by what was built up, but by what fell in. And sometimes, an eruption does not need new magma at all to get started. A tectonic earthquake, a sudden shift in the stress field, miles away from the volcano, can be enough. A seismic wave passing through the crust can change the pressure on a magma body. Just enough, just for a moment, to destabilize a system that was already very close to the edge. A magma chamber, sitting quietly, pressurized, waiting, can be nudged into eruption by an earthquake. It had nothing to do with a reminder that the earth is all connected, that nothing underground exists in isolation. And there is one more thing that can stand between the magma and the surface. Sometimes, magma that has been rising stalls. It loses its momentum. Perhaps because the conduit narrows. Perhaps because the pressure drops. Perhaps because the eruption rate decreases. And the magma, sitting in the upper conduit, begins to cool, begins to crystallize, begins to solidify. Slowly, it becomes a plug, a mass of solidified rock, blocking the vent, sealing the conduit. Like a cork in a bottle, this solid plug can persist for years, for decades, sitting in the upper conduit, while new magma accumulates below it, pressure building quietly against the sealed door. And when that pressure finally becomes too great to contain, the eruption that follows must first remove the plug, which is one reason why some eruptions begin with extraordinary violence. The first explosion, clearing the blockage before the sustained eruption can begin. Now, with all of this happening underground, the surface is not silent. The earth above a restless volcano begins to speak in signals, in signs, in subtle language that scientists have learned over many decades to read. The first and most important is earthquakes. As magma moves, as it forces open new fractures, as it pushes against the rock above and around it, the rock responds. It adjusts. It cracks. Each crack, each small fracture, each tiny slip produces a small earthquake. Most of these are far too small to feel. Barely a tremor, a whisper in the seismic record. But sensitive instruments placed around the volcano detect them, map them, locate them in 3 dimensions. And as the earthquakes cluster, as their locations migrate upward, tracing the path of rising magma, a picture emerges of movement deep in the rock, of something ascending. The ground itself also speaks as magma intrudes into the shallow crust, as new material is forced into the rock. The ground above swells imperceptibly at first, millimeters, then centimeters, the surface tilting outward, inflating, like a very slow, very large breath being drawn in. This ground deformation measured by GPS instruments, by tilt meters, by satellite radar, is one of the clearest signs of magma moving upward into shallow storage. The volcano is breathing in, but not all intrusions announce themselves this way. Sometimes, the rock surrounding the intruding magma is warm enough and soft enough to deform without breaking, to yield plastically, the way warm wax yields, rather than cracking. And when rock deforms this way, ductilely, without fracturing, it produces no earthquakes. The magma moves. The ground inflates, but silently. No seismic signal. No warning in the earthquake record. Just the slow, quiet swelling of the ground above, visible only to the most sensitive geodetic instruments. These silent intrusions, aseismic, moving without sound, remind us that the earth does not always warn us in the ways we expect, that sometimes the signs are subtle, and sometimes they are hidden, and the volcano prepares itself in its own way, on its own schedule, without asking our permission. And all of this, the fracturing, the plugs, the deformation, the silent inflation, the distant earthquakes that trigger unrest, all of it is part of the long, slow build-up to the moment of eruption, a moment that may be hours away, or years away, or centuries away. The earth, making its preparations in its own time. Let that unhurried quality settle over you now. The volcano is not in a hurry. It prepares slowly, carefully, on a time scale that makes human impatience feel very small and very gentle. You have traveled so far tonight, from the mantle, through the rising magma, through the chamber and the mush, through the gases and the viscosity, and now, through the slow, subtle preparations for eruption. You are almost at the surface now, almost at the moment when everything we have watched building finally reaches the air. But not yet. For now, just rest here, in the quiet before, in the slow, patient time of build-up, of preparation, of the earth drawing its breath. Feel your own breath, slow and deep and patient. The volcano is not ready yet, and neither are you. Not ready to wake, not ready to surface. Just breathe and let the ground swell gently beneath you. Just a little, just enough to remind you that everything below is alive and slowly getting ready for something beautiful. Let your eyes stay closed. Let your body stay heavy. We have been underground for a long time now. In the quiet. In the dark. In the slow world of magma and crystal. And pressure. And time. But the earth above the magma is not empty. Not silent. There is another world up there. Just above the chamber. Just beneath our feet. A world of water. And heat. And slow, hissing chemistry. Rain falls. On the slopes of volcanoes. It falls on the summit. On the flanks. On the ancient lava fields. And it sinks into the ground, moving downward through cracks, through porous rock, through the spaces between mineral grains, deeper and deeper, and somewhere below, it meets warmth. The magma sitting in its chamber radiates heat outward, constantly, the way a warm stone radiates heat into the cool air around it. That heat moves through the rock, slowly, in all directions, and when groundwater, descending from above, enters that warm zone, it changes. It heats up. It becomes more reactive. It begins to dissolve minerals from the rock walls around it, carrying them in solution, altering the chemistry of everything it touches. This is how hydrothermal systems are born. Hot water, circulating through fractured rock, heated by magma below, rising along some pathways, sinking along others. A slow, hidden circulation that can persist for thousands of years. And as that hot water moves through the rock, it changes it. Minerals dissolve. New ones precipitate in their place. The rock is chemically transformed, weakened in some places, altered beyond recognition. What was once hard, fresh volcanic rock becomes soft, clay-rich, crumbly, honeycombed by acid, by heat, by the ceaseless movement of hot, reactive water. This hydrothermal alteration, this chemical weathering from within, is one of the hidden dangers of volcanic landscapes. Rock that looks solid from the outside may be deeply weakened inside, transformed by decades of hot water, moving invisibly through it. And sometimes, the magma below heats the groundwater, not just to warm, but to hot, to boiling, to steam. When groundwater becomes pressurized steam, confined within the rock, unable to escape freely, pressure builds quietly beneath the surface. And when that pressure finds a release, the result is a hydrothermal explosion. No new magma reaching the surface. No fresh lava. Just steam. And superheated water. And shattered rock. Erupting violently from a vent that showed little warning. These steam-driven explosions, phreatic eruptions, are among the most sudden and least predictable of all volcanic events, because they require no magma at the surface, only heat and water and confined pressure. But sometimes the volcano breathes, not in explosions, but in a long, continuous, quiet exhalation. In some volcanic systems, magma sits just deep enough, just cool enough at its margins, that it never quite erupts, but it degasses, slowly, continuously, releasing its volatiles upward, through the rock, through the hydrothermal system, into the air above. Fields of fumaroles, vents in the ground, hissing with steam and sulfur, can persist for decades, for centuries, fed by magma that never reaches the surface, that simply sits below, releasing its gases, slowly, patiently, breathing out, without ever erupting. These fumarole fields, those pale, steaming landscapes, white with sulfur deposits, smelling of hot springs and deep earth, are the visible face of a volcanic system that is very much alive, even in its quietest moments. And now, at last, we come to the moment we have been slowly approaching. All this time, the eruption, all of that pressure, all of that accumulated gas, all of that rising magma, finally reaches the surface. And how it arrives depends on everything we have learned tonight. If the magma is fluid, low in silica, rich in gas that can escape gradually, the eruption may be relatively gentle. Lava welling up from a vent, flowing outward, following the slope of the land, moving slowly enough that you could, in many cases, walk alongside it. But if the magma is thick, viscous, rich in dissolved gas, that cannot escape gently, the result is very different. As the magma rises through the final meters of conduit, the pressure on it drops precipitously. The gas that was dissolved in the melt tries to expand. All at once, the magma cannot accommodate that expansion, cannot flow fast enough, cannot release the gas gradually, and it fragments. The melt is torn apart, shattered into droplets, into shards, into particles ranging from large clots of lava to dust-fine ash, all of it hurled upward by the expanding gas at extraordinary velocity. This is a pyroclastic eruption, and the material it produces, ash, lapilli, volcanic bombs, pumice, is collectively called pyroclasts. Fire fragments. The eruption column, that towering white and gray pillar, rising kilometers into the sky, is a mixture of this fragmented rock and hot gas, rising on its own heat, buoyed upward by the thermal energy of the eruption itself. And sometimes, the rising magma meets something else entirely. If a conduit passes through a layer of groundwater, if magma reaches a water table, or forces its way beneath a glacier, or enters the sea, the meeting is explosive. In a different way. Water, flashing instantly to steam, when it contacts magma, expands to roughly 1,700 times its liquid volume. In an instant, that expansion is violent beyond imagining. These phreatomagmatic explosions, magma meeting water, produce some of the most violent and finely fragmented eruptions that volcanoes generate. The magma is shattered, not just by its own gas, but by the explosive vaporization of water around it, producing clouds of fine ash and steam and superheated gas. And what reaches the surface, what flows and cools and solidifies, becomes rock. Different magmas, different cooling rates, different compositions, produce different rocks. Basalt, dark and fine-grained, from fluid, fast-cooling lava. Rhyolite, pale and glassy, from silica-rich flows. Andesite, gray and intermediate, from the volcanic arcs that ring the ocean basins. Obsidian, black volcanic glass, from lava cooled so fast it had no time to crystallize. Each lava flow, each deposit of ash, each layer of pyroclastic material adds to the structure of the volcano, layer by layer, eruption by eruption. The landform grows. The gentle slopes of a shield volcano, built from countless fluid basalt flows, spreading wide and low, like a warrior's shield, laid flat upon the ground. The steep cone of a stratovolcano, built from alternating layers of lava and pyroclastic deposits, growing tall and symmetrical and beautiful, and above all of it, rising into the atmosphere. Something else is happening. The eruption column, carrying fine ash and sulfur dioxide and water vapor, rises high into the sky, sometimes reaching the stratosphere, where winds carry it around the globe. In the dark interior of the ash cloud, something electric happens. The tiny ash particles, colliding, grinding against each other, build up electrical charge. And that charge discharges in volcanic lightning, bright, violet white, flickering within the dark column. One of the most spectacular sights in all of nature. And the gases, especially sulfur dioxide, lofted into the stratosphere, react with water, forming tiny droplets of sulfuric acid. A veil spread across the upper atmosphere, reflecting sunlight slightly, subtly, cooling the earth below. For months or years after the eruption has ended, distant harvests affected by a volcano they never saw or felt or heard. Climate nudged by chemistry injected into the sky from deep below the ground. The ash in the upper atmosphere can disrupt aircraft engines, ground flights across entire continents, close airports, redirect journeys. A volcano erupting in one corner of the world, reaching into the lives of people who will never see its summit, never feel its heat, never smell its sulfur. The earth, connected in ways that are easy to forget. When the sky is blue and the ground is still, let that connection wash over you gently. The long chain of events we have followed together, from deep in the mantle, all the way up, through the crust, through the chamber, through the rising conduit, out through the vent, into the air, into the atmosphere, into the climate, into the world. It is one continuous story, with no true beginning and no true end, just transformation from one form to another, from one depth to another, from one state to the next. And you, resting here, breathing slowly, at the surface of it all, are part of that story too. The air you breathe contains volcanic gases, released over billions of years of eruption. The water in the oceans, partly volcanic in origin, exhaled from the earth over geological time. You are downstream of all of this, downstream of the mantle, and the chamber, and the conduit, and the eruption column, and the slow rain of ash across ancient landscapes. Let that be with you, quietly, as you drift. There is so much more to learn. But for now, let the eruption column rise without you. Let the lava flow in its own time. Let the ash settle slowly through still air, the way your thoughts are settling now, slowly, gently, finding their resting place. The volcano has spoken, and the earth is quiet again, for a while, and so are you. Let the quiet settle around you, like ash drifting down through still air. After the eruption has passed, the violence is over. The column has fallen back. The lava has slowed and cooled. and stopped. And now, in this long, gentle aftermath, we explore what remains, what the volcano leaves behind, and what continues quietly in the deep. But first, let us go somewhere few people ever think about when they imagine volcanoes. Let us go beneath the ocean. Most of the volcanic activity on Earth does not happen on land. It does not happen at the famous mountains, the cones visible against the sky. Most of it happens in the dark, at the bottom of the sea, along the mid-ocean ridges, those vast underwater mountain chains, running for tens of thousands of kilometers, across the floors of every ocean. Here, in the cold and the pressure of the deep sea, magma reaches the surface continuously, quietly, in eruptions that no human ever witnesses, in a world of total darkness and crushing pressure and near freezing water. When lava erupts onto the seafloor, it meets cold seawater, and the outer surface chills almost instantly, forming a glassy skin, while the interior remains molten, flowing onward, inflating the skin from within, like a slow balloon. These are called pillow lavas. And the seafloor, along the mid-ocean ridges, is carpeted with them. Rounded, bulbous, stacked upon one another, in vast fields, stretching for kilometers, built up over millions of years of continuous, quiet, submarine eruption. And in some deeper eruptions, where the magma supply is especially generous, great ponds of lava can form on the seafloor, contained by the surrounding topography, filling low areas, inflating upward, growing slowly, until they overflow, or until the supply from below diminishes, and they solidify in place. Enormous flat sheets of basalt, paving the ocean floor. For most of human history, we knew these eruptions only by inference, by the rock record on the seafloor, by the chemistry of the lavas, by the magnetic signatures frozen into the crust. As it cooled, we knew eruptions must be happening, but we had never seen one until, with deep-sea submersibles and remotely operated vehicles, we descended and watched, and what we found confirmed what we had theorized, but made it real in a way that theory never quite can. Melt rising through the seafloor, glowing faintly in the absolute dark of the deep ocean, witnessed for the first time by human eyes, and in the conduits through which that lava moved. Something else happens that leaves its own record. As magma flows through a narrow conduit, moving fast, the outer edges of the flow, in contact with the cooler conduit walls, experience tremendous shear the fast-moving interior, dragging against the slow or stationary edge. This shearing, this tearing of the melt, can quench the outer surface so rapidly that it becomes glass. Thin, smooth, glassy layers, coating the conduit walls. Or it can shatter, producing angular fragments, volcanic breccia, broken pieces of glassy lava, cemented together, preserved in the rock. A record of violence in a conduit, long since solidified. Now, back on land, or above the great submarine calderas, another dramatic event is sometimes still unfolding, even as the eruption peaks. We have talked about how a magma chamber can be drained, how the eruption draws material upward rapidly, faster than new magma can arrive from below. And as the chamber empties, as the support beneath the roof diminishes, the roof begins to fail. Not all at once, not in a single catastrophic moment, but in steps. The outer margins of the roof, the edges, where the chamber is shallowest, fail first. Blocks of rock collapse inward. The caldera begins to form, one step at a time, each collapse sending a new pulse of material toward the surface, feeding the eruption further. And over time, as the chamber empties and the collapses progress inward, the caldera grows. A broad depression, where a cone or dome once stood, or where the landscape was simply flat, now replaced by a vast circular scar, kilometers across. The roof of a world that no longer exists below. These caldera-forming eruptions, the great ones, like Toba, like Yellowstone in its ancient past, like Tambora, are among the most consequential geological events of the recent Earth, reshaping landscapes, altering climates, leaving deposits of ash and pumice that can be found thousands of kilometers from the source. And in the time between eruptions, the repeated intrusions, the endless injections of new magma into the crust that never quite reach the surface, they too leave their mark. Each intrusion, each dike or sill, pushing into the rock above, lifts it just a little. And over hundreds of thousands of years of repeated intrusion, of pulse after pulse, of new magma arriving and stalling and cooling and being followed by another, the ground above rises slowly, measurably, a landscape inflated from below, fractured by the repeated stress, altered by the heat, and the fluid, and the chemistry of all those intrusions. And then, when no more magma comes, when the supply from below finally diminishes. The intrusions cool and solidify and become rock. This is the Pluton, the intrusion that never erupted, the magma that ran out of energy before it reached the surface and simply stopped and crystallized in place. Plutons come in all sizes. Some are small, a few kilometers across, frozen dikes and sills, and irregular blobs of solidified melt. Others are enormous, batholith scale, hundreds of kilometers long, great masses of granite and related rocks that once were magma, sitting in the crust, crystallizing slowly over millions of years. And the crystallization itself releases energy. When a mineral crystallizes from a melt, when atoms arrange themselves from a disordered liquid state into an ordered crystal structure, they release heat, latent heat, the heat of crystallization. This heat, added back into the surrounding system, slows the cooling of the intrusion, keeps it warm longer than it would otherwise be, extending the time over which the Pluton solidifies, extending the time over which hydrothermal fluids can circulate and react and deposit minerals. A Pluton is not a cold, dead thing. Even as it solidifies, it is a slow, warm engine, releasing heat, heating the water around it, driving circulation, transforming the rock nearby. For thousands of years after the last eruption, and far below the seafloor, where the mid-ocean ridges are releasing heat continuously, something else has found a home. In this volcanic warmth, where hot hydrothermal fluid rises through the seafloor at the deep sea vents, it carries dissolved minerals, sulfides, iron, copper, zinc, and where it meets the cold seawater above, those minerals precipitate, building chimneys of black or white mineral, rising from the seafloor in the absolute darkness, at crushing pressure, in water barely above freezing, and around those chimneys, in that impossible environment, there is life, complete ecosystems, built not on sunlight, not on photosynthesis, not on anything that originates at the surface, but on the chemical energy of volcanic fluids, tube worms, meters long, swaying gently in the hydrothermal current, crabs, pale and blind, picking their way across mineral formations, bacteria, forming thick mats on every surface, drawing energy from hydrogen sulfide, from methane, from the chemistry of the deep earth. Life, sustained entirely by the heat and the chemistry of magma, cooling, far below. These ecosystems, discovered only in 1977, transformed our understanding of where life can exist, of what life requires, of what is possible in the dark, in the pressure, in the cold, in the heat, all at once. And they have led us to wonder about other places, other moons, other planets, where liquid water exists, beneath ice or rock, heated by geological processes. Could life exist there too, sustained by the same volcanic warmth, in the same darkness, by the same chemistry that sustains it here, on the floors of our own oceans? The volcano that we have been exploring all this time is not just a geological feature. It is a source of life, of metals, of climate, of atmosphere, of the very oceans, built up over billions of years, of volcanic outgassing. Everything connects back to the deep, back to the mantle, back to the slow, patient processes we followed from the very beginning. Let that vastness sit gently with you now. Not overwhelming, just present. The tube worms swaying in the dark, the pillow lavas cooling on the seafloor, the batholith crystallizing slowly somewhere deep in the roots of an ancient mountain range. All of it connected, all of it still happening right now. As you rest, you are on the surface of a living planet, a planet that has never stopped building and recycling and transforming and creating since the day it formed. And beneath you, the work continues, quietly, without urgency, without end. Rest now. You have traveled far tonight, from the mantle to the seafloor, from the magma chamber to the hydrothermal vent, from the eruption column to the crystallizing pluton. It is a long way to have come, and you have been such a patient traveler. Let the deep earth carry you now. Let the warmth from below rise gently through all those kilometers of rock and reach you here where you are, warm and still and drifting slowly into the quiet.